Biodevices Without Borders is a University of Bath VIP team that focuses on developing water quality monitoring solutions that are cost-effective, highly sensitive, and scalable.
Our mission arises because of the global crisis of water scarcity and pollution, which threatens our present and, more devastatingly, our future. It is certain that human actions are the primary cause of water pollution, which only exacerbates water scarcity. As highlighted by the UN supportive statements, 2 billion people worldwide lack access to safe drinking water, with only 0.5% of sources on Earth being usable freshwater, much of which is diverted for agriculture. Climate change further threatens freshwater availability due to many disruptions, such as changes in salinity levels, a lack of snowfall, which affects stream flow, and more. Industrial discharges, agricultural runoff, sewage, and oil spills are among the most important pollutants where infrastructure and resources mitigate effects. Therefore, while our work is globally impactful, we aim to focus on sub-Saharan Africa, due to it having significantly higher mortality rates and a dire need for more affordable alternatives.
These pollutants infiltrate water supplies, inevitably changing the water we drink. Therefore, physical, chemical, and microbial parameters must be monitored to avoid ecological and human disasters.
Current water quality testing methods are expensive, time-consuming, and require specialized lab equipment that is not necessarily user-friendly. Lab results often take up to 3 to 5 days. We are trying to solve this problem by lowering cost and time spent on testing water quality with our new device. Our solution to this was a highly sensitive, cost-effective water quality monitoring solution that is fast, scalable, and can facilitate immediate and global decision-making. We named our device the On-Site Aquatic Safety Inspection System, or OASIS. Differentiators of our solution are our ease of use, cost reduction, rapid deployment, and a companion mobile application. We think our solution will be successful because it is much more time and cost efficient than available alternatives. The fact that our OASIS device does not require specialized equipment or training offers significant value to users.
So, when the OASIS device is dipped in water, our sensors activate to test for a wide variety of parameters, including nitrate, pH, and conductivity, which are our most developed sensors. When a voltage is applied to the sensor's electrode, an electrochemical reaction occurs based on the ions present in the water and the nanoparticles on the surface of the sensor. By determining the strength of the reaction and then amplifying the signal through electrical circuits, we can interpret the findings in a microcontroller. Using different nanoparticle variations in the metal oxide for pH and nitrate, we can produce sensors that are sensitive to different parameters. The safety of the water can then be fed back to the user through LEDs on the device, or through a Bluetooth connection with a smartphone, enabling GPS mapping and analysis.
Whilst our initial objective was to provide solutions to support the safe consumption of water, as we progressed and talked with more stakeholders, it became apparent there is a need within other applications such as agricultural maintenance, wastewater treatment, and the empowerment of citizens for local measurement and testing. Currently, we are developing and testing sensors by translating lab-based methods onto printed circuit boards, but clearly there is a need to continue exploring new sensors for greater detection capabilities. Through our open source initiative, we hope to optimize our development to enable our sensors to be manufactured anywhere in the world, facilitating the printing and construction within any environment. However, with any project there are barriers to success, and for our student organization, we are no different. Whilst there are risks to funding, user need alignment, or in the most extreme situation, our device not functioning correctly, we have come up with several strategies to mitigate these effects. Handover training and documentation is paramount for yearly iterative development. Grants and local collaborators can be explored to ensure minimal project growth. Formal co-creation studies can be carried out to ensure alignment of user needs, and sensors will be thoroughly tested, validated, and calibrated to world-class water quality standards to maximize reliability. We are still a new team, beginning our journey in 2021. We have much to learn and are hoping for a fully functional, validated, and field-tested system in 2025. Much of our costs consist of development and fabrication needs, which enable us to facilitate day-to-day prototyping. Testing and validation, which enable us to explore use cases and gather real-world data. and human resources to attract talent and to continue our mission. And whilst we have secured some grants to fund expenses, we're continually seeking new opportunities. Therefore, the success of Biodevices Without Borders can be boiled down into key objectives. 1. Develop a commercially viable device that can analyze water. 2. Get the device to our primary users through open source or industry subsidized channels. 3. Along our journey, implement the device into areas that need it. 4. Establish partnerships to ensure the project's future. And 5. With our device, facilitate local and global policy changes through the empowerment of citizens and regulation of pollutants. On behalf of Biodevices Without Borders, we'd like to thank you for listening to our story.